So we're living in a time when the environmental changes to our planet are controversial but also extreme in some cases. And we need ways of understanding the changes and their severity and their magnitude and rapidity. And Earth observation technology is the only way that we can provide that information. 50 years ago, the idea that we could examine these sorts of things, deforestation, forest fires, the rising carbon dioxide concentration in the atmosphere from satellites would be almost unthinkable, but now it's an everyday part of the life of many scientists who work with this technology day in, day out.
Satellites are extremely important for our monitoring of the state of the climate and the state of the atmosphere, because we can get information about any variations in, for example, atmospheric constituents or specific humidity or the temperature of the planet. And before the satellite era, this was not possible because we couldn't get like a global view, an instantaneous global view of all these different components of the Earth's atmosphere. So it's very important for several aspects, including weather forecasting, because we can get real-time observations and we can elaborate these observations with our computer model, and then we can just do predictions that now go up to 10 days ahead, 15 days ahead, or even a month or a season. Before this was not possible, of course, or let's say that the satellite have greatly improved the accuracy of these models. And likewise, from the point of view of the climate monitoring, having like a long-term series of satellite observations is really enabling us to say something about the state of the climate and possible where the climate is going. And looking also back, we see how it has evolved over the years.
From my own perspective, two of the most critical developments that are upcoming in Earth observation are firstly an increase in the resolution of the data sets that we're able to obtain, giving us information about the surface of the ocean and the details of the processes that occur there at an unprecedented scale. And in addition, combining Earth observation with traditional measurements of the ocean is enabling us to get information about the deep ocean, where instruments dive down through the ocean, taking measurements, and then transmit their data back to a satellite database. Previously, the ocean has been a completely unexplored arena. In fact, it's said that the deep ocean is surveyed less well than the surface of the moon. Earth observation is helping to unravel the mysteries of that unknown universe.
The oceans are incredibly complex. You're taking all of the sciences you see on land, the biology, the chemistry, the physics, the geology, and putting them into the marine environment. So it's a very small number of people working over what is over 72% of the planet's surface. And it's a phenomenally difficult job. The one downside of remote sensing is, of course, it gives us the surface skin, the surface layer. We still can't probe successfully into the deeper parts of the ocean. So we still need to use robotic systems, ships, and models to fill in that gap.
Earth observation also provides you with a global overview of your environment and how it's changing over time. If you think about how we collect data on the ground when we monitor animals, we're only able to go in very specific location, looking at very specific type of animals, plants, species in general. Earth observation allows you to get information up to daily on the whole environment. That is a standardized way of looking at the planet on a day-to-day basis. And that's really the strength of Earth observation, giving you information that is standardized, global and accessible to all.
So we're familiar now with some of these wonderful large-scale global pictures that satellites can provide for us in terms of understanding the environment and the climate and our interaction with it. But of course, we mustn't forget, looking around, that many of us, in fact more than half of us these days, choose to live in environments like this, heavily developed urban environments. And of course, satellite remote sensing has a very strong part to play in that as well. These days in particular, technology's developed to such an extent that we have access to very high resolution satellite data. And when I say high resolution, I mean sub-meter, so 30, 20 centimeter pixels. The type of details that allow us to see individual cars and even in some cases to see individual people. Now those kinds of satellite data these days are increasingly being provided by the commercial sector because the requirement for understanding our urban environment, our impacts on it, how we choose to live, how we choose to build our cities in the future, requires that kind of level of detail. So those are different applications from the kind of global scale pictures that we've seen from space agency large scale satellite observations. So if you like, the commercial sector is able to fill in that gap for these very, very high resolution requirements to show us a picture of our cities unfolding as we build them. So we have access to real-time video in high definition from space these days, and we can see aircraft taking off, and we can see cars and buses moving on bridges. That kind of detail allows us to make planning decisions in the kind of urban areas that we want to live in over the next decades.
So one of the exciting work that is happening in the remote sensing conservation community is the work that showed the potential of very high resolution data to actually detect and quantify the number of animals at a given spot. So work by the British Antarctic Survey showed, for example, that you could detect population and quantify the number of individuals within those populations of king emperor penguin in the Antarctic. And that was a revolution because just using Earth observation, you are basically able to know how many population of this species there are and how many individuals in each population you actually get, which is basically monitoring the whole species over its whole distribution range just using satellite data. This really showed the importance of, for the scientific community to be able to access those very high resolution data. Because imagine the potential in deserts where you could potentially map and detect population of large vertebrates, something that is very difficult right now for us to explore because the cost of those very high resolution data is unaffordable for most conservation NGOs and institutions. So the cost of satellite data is really a major limitation to exploring the complete potential of Earth observation to support ecology and conservation. And this is something that, if tackled, could really help develop further methods and get more information about those remote environments that we need to treasure. This has been well exemplified by the Landsat program. As soon as the Landsat data became free, the rate of use just boomed exponentially. And it is to be hoped that those very high resolution data will become available for free to all the conservation and scientists working on trying to support the protection of biodiversity.
So these new technological developments of very high resolution satellite imaging are being provided by, in many cases, commercial companies, people like Planet Labs and Skybox, that are giving us access to, in some cases, real-time high-definition video, but also very high temporal frequency coverage. We're able to cover large parts of the Earth's surface very frequently at high resolution. Those kind of opportunities also give us a much more global picture at the kind of scales that we're used to dealing with from a local perspective. So although we have global coverage, we're able to address local scale problems. And so data are being made available by companies and by space agencies and by governments that we can all have access to. So this gives us the opportunity for everybody, potentially, to have access to satellite data that can help them understand the interaction that we're having with our own environment and the impacts of climate change and how we can respond to these things in the next few years.
Because we're able to look at areas that are regrowing from deforestation previously and areas that are newly deforested, we're able to estimate how much carbon is emitted or sequestered as a result of these processes. And a really interesting and great data product that's come out in the last year is the Global Forest Change product that was produced at the University of Maryland, and it's online and it's powered by Google, and it's quite easy to use. So it has forest gain and forest losses at a 30-meter scale for the entire globe, and it's very easy to use those products. So it's a great tool for the general public, for policymakers, for educators, and whoever wants that information.
We stand today, I think, on the doorstep of a new era in Earth observation, particularly with the launch, the first of the Copernicus Sentinel satellites, to be followed over the next few years by guaranteed launch now of 6 different series of Sentinels, taking us for perhaps 30 years into the future. And this gives us a different perspective, because typically ESA as a research organization is looking for one-off missions, for understanding, for exciting results. Now, we send missions to planets, we send missions to comets, whereas looking at the Earth, we need to do 2 things. We need to have new ideas, new observations, new types of techniques, things that we weren't able to do 5 or 10 years ago, which tells us new things about the planet, or things about different aspects of the planet we weren't able to study before. At the same time, we need to keep making those observations that we were making before, because they're still important. And so we have something of a dilemma, in a sense. We need to be able to do new things and to be able to continue to do the things we did before. We've developed over the last 15 years or so a strategy for dealing with that, through a series of different programs which we run within the European Space Agency. So broadly speaking, we have 3 main blocks of missions. One which deals with research missions, and so that's what we've done as our sort of traditional role of ESA, science missions, understanding. A second, which is also quite long-standing now, is a partnership with the European Meteorological Satellite Exploitation Agency. And this has built up over some 20-odd years since the foundation of EUMETSAT in 1986. And there's a partnership whereby essentially ESA does the development and they fund the long-term operations and the repeat missions which sustain those observations. And more recently, in the last 10 or 12 years, we have built up a similar partnership with the European Commission in the Copernicus program. And so observations which were first made on ERS-1 or ENVISAT or our earlier research missions are now being repeated and continued through a suite of different Sentinels, Sentinel 1, 2, 3, 4, 5, maybe even Sentinel 6. And these provide the continuity of the data which we first were able to make the observations with ERS-1 or ENVISAT, and now continuing into the future. So we're able to, by this suite of different programs which we would like to maintain, understand how best we can serve the research community and those who need to have long-term observations. And the long-term observations, of course, give us not only measurements of the planet in the long term, but also sustainability. So if people want to start developing businesses and business practices, new ways of observing aspects of the Earth which are important for them, for policy aspects or for financial or for commercial aspects, then they have the confidence to know that these observations are going to be there for 20, 30 or more years, which they never had before.
We know that the climate and the environment of the Earth are changing, and we have to understand those changes and monitor them over time if we're going to make sensible decisions. Earth observation satellite technology, using the approach of remote sensing, is ideally placed to provide the information we need to study the Earth and how it's changing over time, including into the decades to come.